So let me talk a little more about factoring polynomials. There are all these tools that you can learn about, this rational root test and Eisenstein's criterion and Gauss lemma to check when things can be factored, when they cannot be factored, etc. Especially with coefficients in rational numbers or coefficients in integers. We'll probably look at some of that later, but right now we did see some way of checking when some polynomials have factorizations when some don't. For example, I have exercise in the notes worked out. Here's another one. Let's look at this guy. X cubed minus 3x plus 3. Show fx is irreducible in Qx. So if you knew Eisenstein's criteria, this would be immediate, but I sort of have an ad hoc proof in the notes. Now I want to point out that factorization in different fields work differently. Show this thing is reducible with coefficients in F5, for example. So if you reduce coefficients mod 5 and look at it in F5, then it is reducible. Again, factoring amounts to, if you have a degree 3 thing, then to be able to factor it is to have a degree 1 factor, which is same as having a root. So in F5 you have 5 strings, 0, 1, 2, 3, 4. You just try those values and see if something gives you 0, and you'll check immediately that if you plug in 2, then you get 8 minus 6 plus 3, which is 5, which is 0 in F5. So 2 is a root, and that tells you that x minus 2 is a factor. And once you know a degree 1 factor, you can easily factorize it, and you'll find that it actually factors into linear factors. That x minus 2, x minus 4 square. Okay, so that sort of thing can happen. There's this big general result, which is exactly analogous to prime factorization, which says that any non-constant polynomial in fx, where f is any field, can be essentially uniquely written as a product of irreducible polynomials. So this is unique factorization into primes. So let f be a field, then any, I should have said irreducibles. In Z they are called prime numbers, here they are called irreducible polynomials. Any non-constant polynomial in fx is a product of irreducible polynomials. Okay. This is a straightforward induction proof, and this factorization is unique up to rearrangement of factors and up to multiplication by non-zero constants. So let f be a polynomial non-constant suppose, so I'm writing the uniqueness part of this factorization, f is p1 times p2 times pr, and also f is q1 times q2 times QS, where the P's and the Q's are polynomials that are irreducible, polynomials, then first of all R has to be S, and the P's and the Q's have to be the same up to some permutation and up to some constant. Pj equal to Q sum pi j for some permutation pi. So there exists some permutation of the indices such, so this is the permutation group, such that Pj is equal to Qj times some scalar for some lambda j non-zero constant for all j. Okay, so what I mean is, here is a factorization of our f that you saw here. So you had this fx in f5x, let's say. Here is a factorization, x minus 2 times x minus 4 times x minus 4. But of course it's not unique. You could also, so we call this p1, p2, p3. But you could also take x minus 4, x minus 2, x minus 4. Furthermore, you could do even worse. You could, let's see, 2 times 3 is 6, which is 1, right? So you could multiply here by 2. Put extra 2 here and put extra 3 here, you know. Then you get 2x minus 8. 8 is same as 3. And then 3x minus 6. 6 is same as 1. So you could call them Q1, Q2, Q3. Now these guys are not really same as those guys, but up to some permutation, they are the same, and up to some constant. There is extra factor of 2 here, there's extra factor of 3 here. Those are the lambdas. So up to that fudge, the factorization into irreducibles is unique. That's more or less what I wanted to recall about one variable polynomial. There's a little bit about multivariable polynomials. Maybe we can cover that